All right, so the next three examples are examples where the function has a hole in it. Now, in the notes, we know this because these three examples are in a category that says holes. But, when we're just practicing, we're not going to know that we have a hole in our graph necessarily. So, just like we always do, we're going to first start by just plugging in the value at which we're evaluating the limit. So in this first example, I'm going to plug in 3 for x. And when I do that, I get 3 squared minus 9 over 3 minus 3, which is 9 minus 9 over 3 minus 3, which yields 0 over 0. So remember, in the first video, we said, and I'm just going to scroll up since I'm in OneNote and I can, we said that 0 over 0 is an indeterminate form. And so what that means is that 0 over 0, we don't know what's happening there with our function. We cannot conclude that the limit is equal to 0 or infinity or anything like that. So instead, we have to remove the hole. So holes are sometimes called removable discontinuities because we have some algebraic skills with which we can do that. All right, so the first skill is factoring. And this is an example where we can factor either the numerator or the denominator. And in this case, we can factor the numerator. So since x squared minus 9 can be factored into x minus 3 times x plus 3, remember that's called a difference of squares. And then x minus 3 is just our denominator. What we can do is we can remove the discontinuity, and we can do that by essentially canceling these factors of x minus 3. And since I actually changed the value on the right-hand side, I'm going to write an arrow there instead of an equal sign. So the new function that we have is the function x plus 3. So we're going to evaluate the limit of our original function using x plus 3. So the limit as x approaches 3 of, actually we don't really need parentheses there, but we can use them there, of x plus 3, because that's what we had left over here when we canceled, so to speak, our factors of x minus 3 in the numerator and denominator. And so when we evaluate that, we get 3 plus 3, which equals 6. So the function x plus 3 is not the same as our original function because our original function has a discontinuity at x equals 3, and the type of discontinuity is a hole. And again, the way we know that is that when we plugged in 3, we got 0 over 0. That is always indicative of a hole in the graph. So the other function that we evaluated, x plus 3, that one is going to behave exactly like our original function, except it doesn't have a hole in the graph. All right, so that was our example with factoring. Our next example is where we can use a conjugate. So we're going to multiply by the conjugate. And if you forget what that's not how you spell conjugate. If you forget what a conjugate is in math, I'm just going to go out to the side. If I have the expression a plus b, the conjugate is a minus b. So it's essentially where we just change the sign from addition to subtraction or vice versa between two terms. All right, so if I am dealing with this function, again, let's pretend that we don't know that there's a hole there at x equals 5. So the first thing I'm going to do is plug 5 in for x. So the square root of 5 minus 1, all of that minus 2, over 5 minus 5. Well, the square root of 5 minus 1, or the square root of 4, is equal to 2. So our numerator becomes 0, as does our denominator, yielding 0 over 0. And sorry, those are arrows, not like negative 7s. I'm not using an equal sign here because 0 over 0 is not a value. So I'm just going to use arrows to show what's going on here. All right, so for us to multiply our function by the conjugate, if I have the square root of x minus 1 minus 2 over x minus 5, the thing I'm trying to get rid of here is that radical expression in the numerator, and that the presence of that radical is really a clue that we need to use this strategy. So the conjugate of the numerator is going to be the square root of x minus 1 plus 2. And we're going to multiply the top and the bottom of the function by the square root of x minus 1 plus 2. All right, so let's look at what happens on the top. When I multiply the square root of x minus 1 times itself, that yields x minus 1. And then the reason we're using the conjugate should be apparent in this next step. So if I just do this part in my head, if I multiply the square root of x minus 1 times positive 2, I get 2, I'm just going to write this off the page, 2 times the square root of x minus 1. Sorry, I chose the rainbow pen here. I don't know why. But then when I distribute the negative 2 to that first expression, the square root of x minus 1, I get a negative 2 times the square root of x minus 1. So I could write that all out, but those two terms, when we go to combine like terms, since one is a positive and one's a negative, they're just going to become 0. So that's the whole purpose of multiplying the conjugate, for those middle terms to cancel out. And then our last step, we still have to distribute negative 2 to positive 2. So negative 2 times positive 2 is a negative 4. So this is our new numerator. In our denominator, let's not actually distribute. Let's just write our denominator as a product of these two factors. So our original denominator times the conjugate of the numerator. Here's why. These problems are usually kind of like contrived in a certain way to get an expected mathematical outcome. And you might have noticed that our numerator is going to become x minus 5 now. So I'm running out of room. I'm just going to come over here. So when I clean up that numerator, x minus 1 minus 4 is x minus 5. My denominator is x minus 5 times the square root of x minus 1, all of that plus 2. Make sure our fraction bar goes all the way over our denominator. And now I can divide out the common factors from the numerator and denominator. And remember, when you cancel, so to speak, a factor in your numerator, and your entire numerator looks like it went away, remember, you still have a 1 up there, because we can multiply anything by 1. So now we are going to reevaluate this limit. We're going to evaluate the limit of 1 over the square root of x minus 1 plus 2, and we're going to evaluate that as x approaches 5. So we have removed the discontinuity, and the way that we know that we have removed it is when something cancels from the top and the bottom. So when we go up to that first example, the thing that canceled, I hate saying canceled, but I know that you know what I mean when I say that. It's just not very mathematically sound. The x minus 3s, when we got rid of those common factors, that's what removed the whole. That's what allowed us to evaluate the limit. So in this problem, it's the x minus 5s. When we get rid of that, because remember we had a whole where x equals 5, we're getting rid of the factors in the numerator and the denominator that are causing the whole. So now when I plug a 5 in, I don't get a 0 in my numerator and denominator. We still could, but we usually don't. So now I'm going to evaluate this limit, again, by plugging in 5. So now I have a 1 in my numerator, the square root of 5 minus 1 plus 2. So that becomes 1 over the square root of 4 plus 2, or 1 over 2 plus 2, which is simply 1/4. All right, the last strategy is when we have complex fractions in the function in which we are going to evaluate. We have a strategy to eliminate those complex fractions. But again, let's just pretend in this next example that we don't know that we have a hole there yet, because we won't always, in fact, we will never pretty much be told that information. So I'm going to, just like I always do, start evaluating this limit by plugging in 7 for x. So I get 7 over 7, I'm just going to use an arrow here, minus 7 over 7 over, all of that over 7 minus 7. So our numerator becomes 1 minus 1 over 0, which of course yields 0 over 0. So it's at this step when we get 0 over 0 as the outcome from evaluating our limit, that is what tells us that there is a hole in this function at x equals 7. So our third strategy, where we clear complex fractions. In other words, a complex fraction is when you have a fraction in a fraction. So the fractions in the numerator of this function is what makes it a complex fraction. So our goal is to manipulate this function to get rid of that. So if I have x minus 7, or sorry, x over 7, x divided by 7 minus 7 divided by x in my numerator, and again, this is all over x minus 7. What I want to think about is what could I multiply by that will clear that entire numerator? Well, I know that if I multiply by 7, it will get rid of the first fraction because 7x over 7 is just x. If I multiply by x, it will get rid of the second fraction. So because I want to get rid of both fractions, I'm going to multiply the numerator by 7x. And whatever I do to the numerator, I need to also multiply the denominator by the same 7x. All right, so when I distribute the multiplication of 7x over this subtraction, if you want, you can go ahead and write this out, but that first fraction becomes 7x squared over 7. The second fraction becomes, well, it's negative because there's subtraction there, 49x over x. And then the denominator, I'm going to not distribute here because, again, we want to keep this in factored form. We're hoping something will cancel out. All right, so if I look at those two fractions in my numerator, on the left-hand side, the coefficient of that quadratic x squared, that 7 in the denominator of 7 undo each other. On the right-hand side, we have x divided by x. So we could rewrite this as 7x squared minus 49. Nope, I'm so sorry. X squared minus 49. I forgot we eliminated the 7. So x squared minus 49. And this is still over this denominator, x minus 7 times 7x. All right, we have not removed the whole yet because we've not canceled anything from the numerator and the denominator, but we should be looking for common factors. Remember, x squared minus 49 is what we call a difference of squares, and that can be factored as well. I'm just going to do another arrow because I'm running out of room here. So x squared minus 49 is the same as like x minus 7 times x plus 7. And then in the denominator, we have x minus 7 times 7x. You don't really need parentheses around that 7x, but I put them there. All right, so now I notice that in this expression, we have the common factor x minus 7 in the numerator and the denominator. So when we strike those out, when we divide those off, we're really just taking away a factor of 1 there, since those factors are the same. So the new function we're left with is x plus 7 over 7x. So this is going to behave like our original function, but it won't have a hole at x equals 7. So now we're going to evaluate the limit of x plus 7 over 7x as x approaches 7. So now we're kind of just starting over at this point. We're back to the step where we want to plug in the 7. So I get 7 plus 7 on top over 7 times 7 on bottom, which is 14 over 49. And since those have a common factor of 7, we could reduce this to 2/7. So that's our final answer. This limit exists. The value of the limit is 2/7. However, the original function would have a hole in the graph at x equals 7. So it's not continuous. However, the limit does exist.